Video lectures are uploaded to, if you go into the course and click under content, there should be a YouTube, there should be a link for, let me back up. Course material, go into the course materials, content, lectures, and there will be a YouTube link. You click on that YouTube and it should take you straight to my YouTube channel, but it will take you to the soils playlist. Okay, you won't have to search through all of the videos that I upload, because I'm also uploading them for other classes too. That link takes you specifically to a playlist of only the videos for this class. And those videos are done by date. So that was 2000_0125, whatever Monday was. Today when I upload it, it'll be 0127. So that way they'll be in order. If you miss a date, you know which one you missed. Okay? I'm going to be tied to this podium because I left my clicker and I left my stuff. All right, so remember on Monday we talked about this ionic double layer, and I mentioned that it's kind of like when we go into a concert, that there's this constant movement of these ions. Particularly, here we have this double layer of cations, and that on occasion we have water surrounding each one of these possibly, and water surrounding these anions, and one of these two might switch for each other. We might get a negative charge switch in here for a positive charge, which changes the overall charge in this double layer, and we get this movement and this shifting and this friction, and it's always back and forth. So that it could be 1 nanosecond that a cation is in solution, and it could be another nanosecond that a cation is on the solid phase of the soil column. Remember we talked about the cation exchange capacity. Knowing the lyotropic series, you will probably be asked questions about the lyotropic series in that order. What we notice here is that we tend to have a greater charge down to a single charge. So kind of a good way to study for that is knowing that the greatest charge is going to be on the left side, except for the hydrogen, right? But hydrogen bonding is one of the strongest bonds that we can have. So mostly just that it's aluminum, calcium, magnesium, potassium and ammonium have the same, they're kind of the same size and the same charge, and they also have a very similar hydrated radius. So those two in this ionic double layer might switch for each other easily. We talked about anion exchange capacity, knowing that phosphate is held the greatest. Something that might help you remember that, again, is the charge, but we also have another hydrogen associated with that phosphate. So that's going to give it an extra positive charge compared to sulfate, which is also a -2. And then nitrate and chlorine are about the same. They have a large hydrated radius, and so those two are easily exchanged compared to phosphorus. I just kind of introduced the different colloids, kaolinite and smectite. Not that you would need to know much about the allophane and the ammogalites. Those are going to be kind of our volcanic soils. We're not dealing with any volcanic soils around here unless you start going up into Washington State, or maybe you start getting into Alaska, if that's where you would like to go. I'll send you a postcard because I do not like the cold. Remember we talked about aluminum and iron oxyhydroxides, and then our organic matter, our organic substances that have both CEC and AEC, but the overall net charge is negative. We left off with this chart, and someone asked, are we going to need to memorize the chart? And that answer is no. But it would help you to know the net charge of each of those colloids to be able to identify them on a test. So the question might be, which of these 2-to-1 silicate clays has the greatest charge? Vermiculite, cementite, or mica? Which one has the greatest charge? On the top three. Which one is it?
Potentially vermiculite.
Vermiculite, correct.
But not always.
But no, right. So, but I'm just saying, like, the types of questions will be something like that. This 2-to-1 clay has the highest charge. Cementite, fine mica, or chloride? Which one? Which one has the greatest charge between cementite, fine mica, and chloride? The cementite, right. So like it's kind of just being able to identify which one of these has a charge or a CEC of some sort. Which one of these three, vermiculite, fine mica, and kaolinite has the lowest charge? Kaolinite. Right, so just kind of identifying and knowing that we have a cementite. We're going to have, with the capacity to hold about 150 cations or cation charges. But in a kaolinite we wouldn't. And so if you remember from the video, we had the big cup and the little cup. Y'all remember that? The cementite is the big cup. The kaolinite is the little cup. We can't put a whole lot of cations out there, so putting a bunch of fertilizer out there is just trying to put a gallon into a 16-ounce cup. And so now we're going to get into kind of the makeup of these clay structures. So the mineralogy and how these clays stay together and form a structure such that either A, we can drive a vehicle over it, that we can use it for roadbed or building materials, that we can drag a plow through it, and yet it still comes back to some form and kind of stays very consistent. So with the tetrahedral layer, tetra meaning 4, we have 4 oxygens, 3 on the base, and 1 on the top. It looks like a pyramid. I suck at art too, so drawing that on the board isn't really going to do you any good. But anyhow, it's going to look like a pyramid. I'm going to show this in the next slide. Now the octahedral layer is actually kind of 2 tetrahedrals stacked on top of each other. Like kind of if we had a pyramid here and then a pyramid underneath it. And we'll see that again in the next slide. But 2 tetrahedrals together make an octahedral, but they share some of those oxygens, and that's why there's not 8 of them. Everyone good? No, still got a few people. That's cool. Most importantly about the tetrahedral layer also is that we have silicate in the center, which is going to kind of offset the charge of the 4 oxygens. And so oxygen is always -2. The overall charge for oxygen is -2. And so therefore, if we have -8 charges associated with oxygen and +4 associated with the silica, the overall charge of that little tetrahedral will be -4. They drew it much better than I did, or could have, or wish that I could have. So we have 1, 2, 3, 4 oxygens, and then we have this silica in the middle, which is +4. Here we have an octahedral, 2, 4, 6 oxygens, and either aluminum or magnesium in the octahedral. And so they just form, I like to consider this like a peanut butter and jelly sandwich. You had 2 pieces of bread, or maybe even just a peanut butter sandwich. You had 2 pieces of bread, being the tetrahedral sheet, and then the octahedral sheet being the peanut butter. And the peanut butter is what keeps those 2 pieces of bread from separating. So the octahedral layer is what bonds those 2 tetrahedral layers, and this would be a 2-to-1 silicate clay. Smectite, vermiculite, montmorillonite, mica, chlorite, going back to that table. Anyone have any questions thus far? All right. Now maybe this makes a little more sense. That other ones that's for a different mindset. They can see in 3D. I don't see in 3D. I can see this 2D model a lot better. So we have a pyramid on top of these octahedral sheet and this 1-to-1. And so now that octahedral layer is binding that tetrahedral layer. And this is the red kaolinite that you might see on a softball field or a baseball field, maybe a newly established roadbed. If you see a new building, if you go out here on Neal Street going around by Averett, you'll see they're building this new big structure. That red soil out there is a 1-to-1 clay. It will not shift. Everything is held very tightly together by those hydrogen bonds. So there is no expansion, there's no movement. And that's why we don't have a large CEC. The charge only comes from right here. Oh, sorry. The charge in the in a 1-to-1 only comes from the outer edges, not the inside, because everything is held so tightly together, there's no expansion. On a 2-to-1, we have 2 of those layers, the peanut butter sandwich. And if we add water in between, when water enters in between the tetrahedral and the octahedral, it will swell. Anybody seen any of those anybody seen any shrink swell clays where you have these large cracks in the middle of them? Yeah? Broken houses, messed up roads. Water gets in there and causes it to swell like a sponge. And when it swells up, eventually it dries. And it cannot shrink back down. So once it swells, it's over. That's the size that it's going to be. Remember, we're talking about the little cup here. 1-to-1 silicate clays. In the tetrahedral, we have silica could be replaced by aluminum. We'll go over this in a few minutes. This is called isomorphic substitution. I've got a slide for it. Isomorphic substitution. And what happens is when we go all the way back to the rock cycle, when we have that magma come out, when we have those feldspars, that felsic and mafic types of igneous rock, there's magnesium and iron, and then there's silica and feldspars and aluminum. So our CEC is very low, again, because we only have a charge on the very outside perimeter of this clay structure. And so just because we have kaolinite in our field, just because there's a kaolinitic type of soil, doesn't mean it can't be productive. Just because there's only 3 to 15 centimoles of charge, doesn't mean we still can't grow good crops on it. We just have to spoon feed a little bit more so that we can make sure that we keep refilling. We just have to keep going back to the fertilizer fountain a lot and refilling our cup up. But because they don't shrink and swell, they are really good for foundations. So, next question might be like, which one of these would you expect to see as a road bed? Kaolinite, cementite, or vermiculite? Kaolinite. So understanding and knowing the characteristics of these soils will help you be able to make assessments about your management plan. When you get a job and a boss says, "Hey, here's this new tract of land, tell me about it. What can I do on it? What are some of the things?" And throughout this class, we'll teach you what type of soil it is, like whether it's a silty clay or a clay loam. You will know if it's a cementite or a vermiculite or a kaolinite. You'll be able to determine the CEC. You'll know the water holding capacity. All of a sudden, you'll have this list of things that you can tell your boss, and they'll go, "I am so glad we hired them. I am getting my money's worth." So here we have this being the tetrahedral layer, and this being one octahedral layer, so a 1-to-1 clay. And remember now, we're talking microscopic. Like they had to go look at this underneath a scanning electron microscope to determine this clay structure. So they're very small. Remember, colloids are going to be something you can't necessarily pick out. So we have this 1-to-1 stacked on top of another 1-to-1, that's stacked on top of another 1-to-1, stacked on top, stacked on top, stacked on top, and we get this sheet of a colloid that is finally something that you can pick up. Let's say it takes a million of these layers to make up a piece of soil that you can actually pick up. Now, some water may make it in between these two 1-to-1 layers, and there might be some movement, but not a whole lot. Not enough to cause your foundation to crack. Not enough to mess your road up. Now we're talking about the big cup. They have a high negative charge because of that isomorphic substitution in the upcoming slides. So in the tetrahedral, we will have that silica replaced by aluminum, and because we have a change in charge between positive and negative, we'll have a change in charge in the overall net charge of that structure. You'll need to know that in the octahedral, aluminum can be replaced by magnesium, and that will cause an overall change in the structure and the charge. And so here's the easy clue. Here's the easy clue for this. When you see something with a high CEC, it's not kaolinite. And so this water that gets in between those layers is what causes that swelling. And when the water leaves, the structure is kind of stuck there. And then when you put weight on it, that structure crumbles. So it did swell up and kind of filled that space, but there was a whole lot of pore space in there, not enough structure to maintain the integrity of that soil, and it'll shake and move and it can collapse. So we call those shrink and swell. Here's just a kind of diagram to explain. We have our 2-to-1 on top of a 2-to-1, and water gets in between those 2-to-1, each of those 2-to-1 layers, and causes some expansion. And then also there's water coming in between. Water can move in between here, so now we get twice the expansion. We get the expansion in the first 2-to-1, expansion in the second 2-to-1, and then we get water that pulls them apart even further. And so eventually those charges get to be too far apart, and now you don't have a consistent CEC and it's broken. The important thing to know about these micas, and I haven't really ran into many of these soils around at least the Mid-South, but there can be a problem when we have this expansion and we get that ionic double layer that happens, and we have a lot of potassium in that area around those negative charges, that the potassium will be attracted in between those two double layers. When the water leaves, and it traps that potassium inside that structure. It's trapped there. It cannot come back out until you wet it again. Then it'll swell, and then you might get some of that release. So micas are known for high potassium fixation. Remember just a couple of slides ago that we said that potassium and ammonium are kind of the same. They're equal and they're attracted to soil colloids. So guess what else could get fixed in this type of soil? The ammonium ion. In chlorites, which I've yet to encounter myself, we have our 2-to-1 and then a 2-to-1, another octahedral in between there, and that takes up the gap in that charge. So there's no expansion. All the charges are taken up and they're held very tightly, and they just don't swell very much. And so then just an overall view going from kaolinite all the way to chlorites. This lab will be beneficial for determining which type, for identifying the different types of clay minerals. Hint, hint. So being able to know what the CEC is, some of those characteristics, some of the, like a mica has this potassium fixation. That should be the dead giveaway for that one. When you see potassium, you'll think of mica with a K, right? Mike, one way to remember that. Kaolinite, going to be the smallest one. But this will be beneficial for determining identifying the different types of clay minerals. We also talked about aluminum and aluminum and iron oxyhydroxides. They don't have a tetrahedral or silica. These are our oxasols. Someone asked last week or Monday about, they said that the soils were mostly positive in that video that we watched. Well, because it's only dominated by aluminum and these oxygens, these hydroxyls on the edge here, we don't get very much change in charge. So however that formed, that's the charge that it is. There is no isomorphic substitution. And because aluminum is a +3, it's going to have a more positive charge compared to a SMEC type. Good, Hunter? It is Hunter, correct? Steven. And I think that's Michael. I don't know why I was thinking. I have two Smiths in here. Is the other Smith in here? I know I got one. You're Michael, correct? Okay. Hunter Smith?
He don't have a class anymore. He chose to do this online.
Cool. And then finally we have our humic substances. There are positive and net charges in this organic structure. Anyone had organic chemistry yet? How'd that go? You know, you don't have to take it anymore, do you? You took your C and rolled out, didn't you? Don't worry, so did I. Organic chemistry sucks. But man, there are people who love trying to figure out the structure and where the charges go and how that all works. We're not those people. All right? We just have to understand that there are these organic substances in our soils that play a huge role. It seems to be the things we understand the least have the most impact on our soils. And we don't understand why. We don't understand how. We just know that they do, and we're just continuing to try and figure that out. But the overall charge of this entire molecule is negative. It may have some positive sites, may have some negative. All right, now we're going to get into this isomorphic substitution. I cannot express this enough. This is not about the same charge. That is not what isomorphic substitution is about. Now, it's possible that two of the same charges can isomorphically substitute. I don't think anyone would ever want to hear me say isomorphically. None of my major professors would ever want to hear me say that. But remember, we talked about potassium and ammonium being equal in that lyotropic series, and that they can both get caught in that the inside the micas, and they can both be trapped there. Those are isomorphic cations. They are about the same size, and therefore they can fill the same space. So isomorphic is about space and size, not about charge. Because if it was about charge, then if it was only one charge for the other, then there would be no change in charge, right? Because if you put $50 in your bank account and then take $50 out, then the balance is even. So isomorphic is more about you you get to fill this same void, but the charges are different, and therefore we get a change in the overall net charge of this structure. And if y'all noticed, I put tetrahedral and octahedral, and which two ions substitute the most for those in those two structures. I know y'all have written it at least 3 times. All right, so let's look at this. I kind of alluded to this in the beginning. We have oxygen, which is always worth -2. And I say worth just because in math, the overall is that when you see oxygen, there will always be 2 negative charges on that. And if we have silica 4+, the overall net charge of that tetrahedron is 4. Simple math. If we look at the octahedron, which is comprised of 6 oxygens, 6 times -2 is 12, plus 3 for the aluminum, the net charge is 9. So now if we add those up, we got 2, 4, 6, 7. In the tetrahedral layer, 2, 4, 6, 7. 7 times -2 is 14. I did this math on a whole overall. All right, cool. So we have 7 in the top, 7 oxygens in the top, 12 and 17. So 17 oxygens, each worth -2, gives us -34. -34. Those are our negative charges. We've got 3 silica, each worth 4 plus 4. 4 times 3 is 12. And we have 4 aluminums times 3, which is 12 also. The overall net charge of this structure is -10. I saw some eyebrows. Saw some eyebrows change a little bit. We're going to do some more of it. So along the top we have -14. Plus 12. 5 oxygens to be -10. 4 aluminums to be plus 12. 5 more oxygens, -10. 3 silica, and then finally another 7. The overall net charge is -12. And what I'm trying to demonstrate here is the difference when we have this isomorphic substitution. And so we see here that same structure, we just isomorphically substituted aluminum for silica in the tetrahedral and magnesium for aluminum in the octahedral. Silica and aluminum in the tetrahedral. Magnesium and aluminum in the octahedral. Everyone kind of following this at least somewhat. Okay. Here's the question. Is it possible for, do you think, like, is someone in the audience or in the class going, well, what about if magnesium and aluminum can substitute in the octahedral, well then why couldn't magnesium and silica substitute in the tetrahedral? Because if aluminum and silica can substitute and magnesium and aluminum can substitute, how come we can't get that in the tetrahedral? The charge is too great. The charge is too great in here, in this tetrahedron, for this magnesium 2 to isomorphically substitute. But in the octahedral, those charges are spread out more, and magnesium can kind of worm its way in. And so just by substituting aluminum for silica in the tetrahedral and magnesium for aluminum in the octahedral, we get an overall change or an increase in the CEC of -10. So our cup just got a little bit bigger. Right? Now we're into the medium. So isomorphic substitution, same size, not the same charge. Everyone good here? Next, we have the pH dependent charge. So this is going to be related to pH. When we change the pH of the soil, we're changing the electromagnetic. We're changing the way that the aluminum and some of the other ions interact with each other, right? And I'll ask you this several times throughout the class. The three sources of pH dependent charge are going to be functional groups of organic matter, aluminum and iron oxides, and broken edges of clays. Functional groups of organic matter, aluminum and iron oxides, broken edges of clay. And now the broken edges of clays is really kind of this theoretical thing where, remember I said that we're scanning electron microscopes and we're checking out for a broken edge at 1 angstrom, which is extremely small. So we typically won't deal with those. But the functional groups of organic matter and those aluminum and iron oxides, we will. Where'd it go? Aluminum and iron oxide. And so because there's no silica or any other ions, there's no isomorphic substitution. The charge is all taken up. Nothing else will fit in there. Functional groups of organic matter, which we're about to go over how that works. So this big long thing that we throw up at every time we see or hear anything organic chemistry related. You don't necessarily need to know that that's a carboxylic group, okay? Because this is organic chemistry. You don't need to know that it's an alcoholic group or a phenolic group. What's most important is that we do know that there is this hydroxyl or alcohol of some sort hanging off of this functional group of organic matter. This is where we're going to get this change in charge. So currently right now, this little molecule right here, this functional group, this piece of organic matter is, the overall net charge of it is negative, but currently right now there are no charge. This is an equilibrium right here, right? Because there's no, except for this one isn't in equilibrium, right? Because there's a positive or a negative charge associated with it. So as a soil becomes more alkaline, we get an increase in hydroxyls. And as the soil becomes more acidic, we're increasing the hydrogens. Now this is going back to chemistry, that pH being a log function of the hydrogen concentration. Y'all remember that kind of? That the more acidic a substance is, the greater the hydrogen concentration. The more alkaline a substance is, the greater the hydroxyl concentration. So I was explaining this to my soil chemistry class. Do we have any people who farm here? Yeah, okay. So here's what happens, right? At the end of the growing season, we're likely to throw about 2 tons of lime out and let that kind of do its thing over the winter. Then we'll come back in the spring, we'll take a soil test, and we'll see what we got out there. We may need to add some more lime or not. One way or the other, though, we know we need to add lime, right? because the soil becomes acidic because we've applied fertilizer. So this is a process that you will encounter if you're growing crops. You apply fertilizer, it makes it acidic, you have to apply lime. When you apply lime during that process, hydroxyls are added back to this soil solution. And those hydroxyls are negative. And because soil always, life in general, is always trying to reach this equilibrium, watch now, those hydrogens will dissociate from those functional groups of organic matter and form a water molecule. Now this isn't like the type of water molecule that we like get from the tap or whatever. This is like a Avogadro's number is 6.02 times 10 to the 23rd, right? We're talking about like one of those little 6.02 molecules. When that equilibrium happens in the soil, now you can see that we have this negative charge because that hydrogen left. The hydrogen dissociated, and we're left with this negative charge. So which means we can hold on to another cation. So now we've just upsized to the medium cup when we added our lime. Right? Okay, and so then what happens? We go to come springtime, we add a little bit more just to make sure that we got it through the season, because we know we're going to add fertilizer. When we add the fertilizer, the processes that happen from ammonium to nitrate add more hydrogens back to the soil. That's why our soils become acidic over the growing season. So, here we have this at March, and we've added our lime, and those water molecules have formed because we need to find this equilibrium with the hydrogens that are in the soil that are left over. In this functional groups, this organic matter, we have these negative charges hanging out that allow us to hold on to more cations. Right? Over our growing season, we add fertilizer and we add hydrogens back to the soil. It's a natural process. You didn't do anything wrong. Remember, we're trying to get food out of the ground. Because we're trying to find equilibrium in the soil, those hydrogens will now reassociate with the hydroxyls or the oxygens that they just came from. And this constantly happens back and forth throughout every growing season, throughout every single day, actually. Technically, this is happening constantly. We're getting this change until this soil gets to equilibrium. But soil is constantly moving. It's a living thing. Those molecules are moving all the time. Remember that ionic double layer. And we're all trying to get into the concert, and we all want the best spot by the stage. So each one of these hydrogens is now moving to associate. We still got some hydrogens left in the soil, but they're in more of an equilibrium, and our pH gets to be about 6. If we continue to add fertilizer without changing the pH of our soil, we're adding more hydrogens back. At some point, we flood this system with so many hydrogens that they have to go somewhere. And because of the change, and I don't necessarily expect y'all to be able to regurgitate most of this, but from organic chemistry, this phenolic ring, these charges change. They do rotate. They're not always right there. And the change in this charge distribution is directly related to some charge change in a piece of some of that other structure that happens right here. And so if the charge changes and there's an opportunity for a half of a charge to become more negative, that hydrogen will start to move over there. It may be weakly held there. It may just be slightly attached, and when the pH changes over here, it might dissociate again. It's constantly changing, all the time. It would probably be a good idea to go back and write down what I said so that you understand pH dependent charge. Like I said it slowly and I said it over again. I'll probably go over it again on Monday. It's one of the most important things that we deal with in nutrients in our soils. And it's not that your boss is ever going to ask you about pH dependent charge, but it's that you understand we can manipulate our soils by adding lime to increase our CEC. We can increase the size of our cup by adding lime, and this is why. The boss says, I don't understand why I can't grow any crops. How many of y'all have gotten this? Oh, you're an ag? Can you tell me what's wrong with my tomatoes? No, I can't, because I haven't even seen your tomatoes. Are you sure you've even grown tomatoes? Did you get the right kind? What's your soil type like? So the number one thing you need to do is take a soil sample. The very first thing I tell anyone that says, hey, can you tell me what's wrong with it? I said, did you take a soil sample? Until you give me a soil sample, I can't tell you anything about it. Once I know the pH, we can start adjusting some of these things. Okay? I'll see y'all in the lab this afternoon in Oakley 9. Thank you so much for your time.